Welcome to the last day of the DSC Jaipur Literature Festival. We begin with Big Bang, a session sponsored by the Hindustan Times series with Singh and Madhu Trehan. Please give them a very warm welcome.
Singh, controversial and fascinating. I would call him a rock star scientist, and not because of his hair. When some Doon School students got to know, that some friends of mine, that they got to know that I was going to introduce you, they were ecstatic. Apparently, they were your students when you taught for a couple of months at the Doon School between Imperial College and your PhD. They haven't forgotten you. Simon writes about mathematical and scientific topics, which are to the average reader inaccessible and often incomprehensible. But he writes in a language and style that makes it real and easy. He has received numerous awards, and in 2003 was made Member of the Order, I really needed to say this, Member of the Order of the British Empire for services to science, technology, and engineering in education and science communication. His books, Fermat's Last Theorem, he also made it into a documentary that won a BAFTA award and was nominated for an Emmy. In his book, The Code Book, Simon explains the science of codes and the impact of cryptography on history. The Code Book brought Simon back to television. He presented The Science of Secrecy, a 5-part series for Channel 4. His latest book, Medicine on Trial, is about complementary and alternative medicine, of which he is not a fan of, right? And for which Simon was sued by, amongst others, the Chiropractors Association. But the book he will talk about today, Big Bang, is about those who reached the conclusion of the Big Bang theory and how they got there. In his trademark style, Simon explores the remarkable stories of the people who put the pieces together. As he says on his website, the battle for cosmic truth would involve politics, religion, bitter disputes, nuclear physics, satellites, telescopes, a supposed echo from the Big Bang, and remarkable serendipity resulting in one of the greatest adventures in the history of science. I think you're in for a treat. Simon is here to talk about this book.
Thank you very much for that introduction. Thank you very much for inviting me here to the Jaipur Literary Festival. I'm going to talk for about half an hour, and then we're going to have a short discussion on the stage, and then we'll have plenty of time for questions from the audience, because obviously cosmology and the Big Bang is a massive subject, and I can only really touch on a few details. So whatever I gloss over or whatever I miss out, you'll have a chance to ask questions in the second half. First of all, why did I write a book about the Big Bang? There are so many books about cosmology. Maybe it's one of the most popular areas of science writing. For me, this was important because for thousands of years, ever since humans have been around, we've wondered, where did everything come from? And we've had theological ideas, we've had spiritual ideas, we've had creation myths. Every society, every culture has had a theory about where everything around us came from. But we are the first generation of humans on this planet to have a theory that is beautiful, elegant, and verifiable. It's not perfect, it's not complete, but the theory is compelling. And so I think we should just celebrate that as a generation. And I wanted to explain, what is the Big Bang Theory? Who came up with the Big Bang Theory? And why do we think it's true? And that's what I'm going to talk about this morning. What is the Big Bang Theory? Who came up with the idea? And why do we think it's true? So first of all, who came up with the idea? Well, this is Georges Lemaitre. And he was a Belgian cosmologist in around the 1920s. And in the 1920s, the standard idea in science was that the universe had been here forever. That's a nice idea, because if the universe has been here forever, you don't need to worry about when it was created. It's been here forever. Who created it? Well, nobody. It's been here forever. How was it created? Well, it wasn't created. It's been here forever. So that theory is a very comforting theory for science. But there was no real evidence to back it up. And so Lemaitre came along And he said maybe there's another idea. Maybe the universe was created in a finite time ago. And he imagined all the matter in the universe compressed into what he called a primordial atom. And that atom, containing all the atoms in the universe, exploded. And the debris flew apart, and the debris formed galaxies, and the galaxies and the stars would still be flying apart if his theory was correct. Okay? Now, he didn't have any evidence for his theory. It was just a hypothesis. But in a way, the other idea, the universe that's been here forever, is also just a hypothesis with no evidence. But when he put forward his idea, it was really rejected. He got a very bad reception. And one of the reasons for that, as you can maybe just see in the picture, is that Lemaitre was a priest. He was a Catholic, a Jesuit priest. And people said, the reason you want creation is because creation implies a creator. And he said, no. He said, there are two ways of arriving at the truth, and I decided to follow them both. So he meant that he was religious, and he used his religion to study spirituality and ethics and morality, but he was a scientist, and he used science to understand the universe. And he didn't mix up the two. If he wanted to know about ethics and morality, he didn't do an experiment. If he wanted to understand where the universe came from, he didn't read the Bible. So he kept the two separate. And he said, I like the idea of a Big Bang universe because it might be right. It might be worth exploring. But still nobody accepted it. He met Einstein one day at a conference, and he explained to Einstein, I have this idea. He didn't call it Big Bang. He talked about a day without a yesterday, a very poetic description of this moment of creation. But Einstein wasn't impressed. Einstein's reaction was, your calculations are correct, but your physics is abominable. Now, by this, what Einstein meant is that in science you have two things. You have mathematics and equations and theory, and that's what we might call the calculations. He said, on paper, your calculations look okay. But in reality, reality is the physics, if you could test your theory, it would be wrong. And this is a really important point in science. If you have a theory, you must check it. You must be able to check it against reality. I'll give you an example of this. If you don't test your theories, your mathematical theories against reality, they can be nonsense. And just to show you what I mean by this, I've been working on a mathematical theory of my own. According to my theory, I think I can prove that the Teletubbies are evil. Okay? The BBC created the Teletubbies with a lot of time and money, so the Teletubbies are a product of time and money. Now, we all know that time is money, so we can substitute back into the equation, which gives us money times money, or money squared. We also know, and it's often said, that money is the root of all evil. Therefore, money squared is evil, and therefore the Teletubbies are evil, okay? Now, it's only a theory, it's only mathematics. If you want to prove this, you have to do an experiment, and I did an experiment last week, and they are indeed evil. So if Lemaitre was going to prove his theory, he had to have evidence. And in astronomy, the way you find evidence is by building telescopes and by looking up at the stars. And the crucial evidence for Lemaitre came from this telescope. This is called the Mount Wilson Observatory in California. And it was built, I think, in the 1920s, when Los Angeles was a very small town. There was no light pollution. It was built on the mountains outside Los Angeles. And this was the biggest and best telescope in the world. And not only was it the biggest and best telescope in the world, it was operated by the best astronomer in the world. This is Edwin Hubble. Hubble today is famous because of the Hubble Space Telescope. And that telescope, which flies above us, orbiting the Earth, is named after Hubble because he was such a great astronomer. Not only was he a great astronomer, he was very charismatic. People would travel all the way to the mountaintop to meet Hubble and to shake his hand, to meet the great man who was exploring the cosmos. And in fact, his future wife, Grace Hubble, met him when she went to the telescope to do a tour of the mountain. And she saw Hubble standing there in the distance. and immediately she was captivated. The moment she saw him, well, she went home that night, and in her diary, she described him as an Olympian, tall, strong, and beautiful, with the shoulders of the Hermes of Praxiteles. There was a power channeled and directed in an adventure that had nothing to do with personal ambition. So she was clearly smitten with him. Unfortunately, she was already married at the time, and she was married to a geologist. Now, being married to a geologist is never very pleasant. But a few weeks later, her husband was on a field trip. He fell down a mine shaft and was killed. So there's kind of a happy ending there. So what Hubble was interested in was galaxies. So here's a picture of a galaxy. We live on the Earth goes around the Sun is a star, and the stars congregate in these spiral galaxies. Each galaxy consists of about 100 billion stars. This is not our galaxy because we're inside our galaxy, so we can't really see our galaxy. But we can see other galaxies, and we can see that they're very similar to our own. And Hubble was interested in these galaxies. And as I say, there are 100 billion stars in every galaxy, and we can see about 100 billion galaxies. So that's why we think there must be life, because with so many stars and so many galaxies, either way, it's incredible. If we're the only life form, that's incredible. If there are other life forms, that's incredible too. But we think there must be other life forms because of this sheer multiplicity of stars and the sheer multiplicity of galaxies. In fact, here's a picture taken by the Hubble Space Telescope. Each one of those dots, each one of those tiny smudges is a galaxy. Each one of those galaxies, 100 billion stars. What Hubble wanted to know is, what do these galaxies do? We know they spin around like Catherine wheels, but do they move towards each other? Do they move away from each other? Maybe they don't move at all. Maybe they just move randomly. That is what Hubble wanted to know. Now remember, Lemaitre said there was a big explosion and the debris flew outwards. If Lemaitre is correct, the galaxies should all be flying apart. So by measuring the motion of the galaxies, Hubble was going to test Lemaitre's theory. Now what did he discover? Well, first of all, before I tell you what he discovered, how do you measure the motion of these galaxies? We can't physically see a galaxy moving. They're too far away. It's impossible to measure this motion directly. But what you can see is the light from the galaxy. So light is a wave. If it's a long wave at the top, we call that red. If it's a short wave, we call it blue or violet. If it's very short, we call it ultraviolet. And the galaxies emit these light waves. Now we know what colors a galaxy should emit, because galaxies are made of hydrogen and helium and oxygen and nitrogen, and we know what colors these elements emit. So we have a standard idea of what every color from every galaxy should be. But if those galaxies are moving, then the colors will change. Let me show you what I mean. Here is a galaxy. It's emitting light, and it's moving in that direction. Now, behind it, the light waves get stretched, and in front of it, the light waves get compressed. So if I'm emitting light, you can imagine how this way the light is being compressed, behind me it's being drawn apart. So if I'm behind the galaxy, looking away, the light will be longer wavelength than it should be. That galaxy will appear to be redder than it should be. If I'm in front of the galaxy, the waves are being compressed, the light waves will be bluer than they should be. So by looking at the galaxies, are they bluer than they should be? They must be coming towards me. If they're redder than they should be, they must be flying away from me, okay? That is how you measure the motions of the galaxies. Now, what did Hubble find? Well, these are 3 galaxies he measured, and I've written in the distances. The first galaxy he looked at was redder than it should be. If it's redder than it should be, it must be moving away. And the exact speed it was moving away was 6 billion kilometers a year. The second galaxy is further away. It was even redder. So it's moving away even faster. Third one, even redder still. It's moving away even faster still. 730 billion kilometers a year. To give you an idea what that means, an aeroplane traveling at that speed would go around the world in just a few seconds. So these are phenomenal objects traveling at phenomenal speeds. But it's not the speed that's important. What's important is that every galaxy is redshifted. Every galaxy is racing away. And that is exactly what we expect from Lemaitre's Big Bang. Explosion, debris flies apart, debris forms galaxies, galaxies fly apart. This is what we are seeing. Every galaxy in the universe is flying away. Okay? So this is the crucial observation, the first evidence that suggested that Lemaitre might be correct. But still, not everybody accepted his idea. And that's okay, because in science, people come up with new ideas all the time. And they come up with a little bit of evidence all the time. And you can't just accept every idea on one piece of evidence. And it's right that the scientific establishment is skeptical and says, okay, one piece of evidence is okay, can you find more evidence? Or maybe your telescope was faulty, or maybe you didn't measure enough galaxies. So people challenged Lemaitre. One of the people who challenged him was this gentleman here, Fritz Zwicky. And Fritz Zwicky said, he said, you know, I'll mention 2 or 3 things about Fritz Zwicky. He's an interesting guy. One thing I'll mention about him is he was very grumpy. You can see from this picture, he doesn't look very happy. And he would invent insults for people. So if he didn't like somebody, he would invent an insult specially for them. And my favorite insult that he invented was when he once called somebody a spherical bastard. By this he meant a sphere is a geometrical object which looks the same whichever way you look at it. And a spherical bastard is someone who's a bastard whichever way you look at them. So that's the first thing about Zwicky. Second thing about Zwicky is that he said to Lemaitre, okay, the galaxies look red, but maybe that's not because they're moving away. Maybe the light from the galaxies is being scattered. As the light comes towards us, it will meet gas and dust. And when the light gets scattered, it loses energy. When light loses energy, it looks red. Okay? So he was saying the redshift is not due to the motion of the galaxy. The redshift is due to the scattering of the light. Okay? And that's a perfectly fair criticism. So he said to Lemaitre, go away and get more evidence. If you can come back with more evidence, then we will believe you. And he kind of knew what he was talking about. He was a maverick. He came up with radical ideas. He came up with the idea of dark matter. The idea of dark matter is that there is stuff out there in the universe that we cannot see. Now, how do we know it's there? Well, we know it's there because it pulls other stars towards it. So it exerts a force, but it doesn't exert any light. So that's why it's dark. And when he came up with his idea, people said he was crazy. And he had to go away and he had to get evidence and more evidence and more evidence until he could persuade the scientific community that he was right. The scientific community is very open-minded. Doesn't matter how crazy your idea is, if you can come up with evidence, the scientific community will embrace your idea. So Zwicky was saying to Lemaitre, you need to go away and get more evidence, and then if you have that evidence, we will embrace the Big Bang. And so Lemaitre had to go away and get more and more evidence. In the meantime, I should explain there was another idea that was emerging. An idea that supported the idea of a universe that had been around for a very long time. It was developed by 3 people working in England. Fred Hoyle on the right, Tommy Gold on the left, and Herman Bondi in the middle. They pretty much accepted that the universe was expanding. Now, if the universe is expanding, then in the past it must have been smaller, in the past it must have been smaller, in the past it must have been very dense. So, if Lemaitre is correct, the universe has changed density over time. Now, they didn't like that idea. They wanted a universe that didn't really change. They could accept the expansion, but they didn't like the idea of change. And so they thought, how can something change but not change? How can an object evolve but still stay the same? And they were thinking about this, and it was the Second World War. Actually, the Second World War just ended. And they went to a movie theater, and they saw a film called Dead of Night. And The Dead of Night is a film, it's, I think it's about 6 different short stories. And the film starts with an architect, a young architect. He wakes up one morning, he gets out of bed, he washes his face, he gets dressed, he goes outside, he gets into his car, he drives into the countryside. He visits a house where he's giving some architectural advice, and they open the door, and when he goes into the door, he says, "This is really weird, because I recognize everybody in this house. I've never met you before, but I recognize all of you. But I've never met you." And one by one, everybody in the house tells their own weird story. And that's why there are 6 short stories. And when the final person tells their story in the house, when they've just finished their story, they walk up to the young architect and they grab him by the throat and they begin to strangle him and they begin to throttle him to death. And just as he's about to die, he wakes up and he gets out of bed. He washes his face, he gets dressed, he goes outside, gets into a car, goes into the countryside, goes into a house, opens a door, and says, "This is really weird. I've never met you before, but I remember you." So here you have a story that evolves, but kind of stays the same. So could you think of a physical object that evolves and stays the same? One example is, this is called a lenticular cloud. I think this one is over Mount Fuji, maybe. This cloud will stay there all day. Now that's weird. How can a cloud on the top of a mountain sit there all day? It's very windy on the top of a mountain. This doesn't seem to make sense. What's happening is that air is coming up the mountain, freezing and adding to the cloud. The cloud moves along a little bit. At the other end, a little bit of the cloud comes down, warms up and evaporates. So the cloud is on a conveyor belt, with new bits being added here and old bits fading away here. So the cloud is changing and evolving, but it stays the same. It's the same with our bodies. I think about maybe every 6 months, nearly every cell in our body is replaced. Every cell is changed with a new cell. And yet we stay the same. I'm still me, you're still you. So things can change and yet stay the same. And so Bondi, Hoyle, and Gold, the 3 gentlemen I mentioned at the beginning, began to think of a universe that was like that. And this is what they came up with. Each of these dots represents a galaxy. So with a Big Bang, the galaxies move apart. And the universe gets bigger and more spread out and less dense over time. With the Bondi, Gold, Hoyle model, the universe expands, but just in between the galaxies, new matter is created, which forms new galaxies. So this is actually pretty much the same as this. The overall density of the universe is the same. If the universe is infinite, it can keep expanding, it can keep creating new matter, nothing really changes. So you had 2 rival ideas. The Big Bang, the steady state with new matter being created, and then the old idea of the universe just never changes at all. And there was a big argument, a big conflict over which of these theories was correct. Lemaitre had a little bit of evidence, the others had a little bit of evidence too, but there was no clear-cut winner. Then these 3 gentlemen came along in the 1940s. This is Ralph Alpha on the right, George Gamow in the middle, and Robert Herman on the left. And these were 3 physicists in, I think, Washington. Well, they moved around a bit, but essentially they ended up in Washington. And they liked the idea of the Big Bang. They said, there's a little bit of evidence in favor of the Big Bang, and emotionally we like the idea. Let's see if we can find some evidence for it. And they made a prediction. They said, what would the Big Bang have been like at the very, very beginning? We know how much matter is in the universe today, so let's squish it together. We can work out the temperature of the universe, we can work out the density of the universe, we can work out the pressure of the universe at the very beginning. And we can work out from that Big Bang every bang has a blast of radiation. The Big Bang also has a blast of radiation. They calculated the radiation that should have been emitted from the Big Bang. And they said, if the Big Bang really happened, that radiation should still be here today. And if you look up into the universe, you should see radiation everywhere. And they predicted that it would be microwave radiation, just like the microwave radiation you get in your kitchen cooker. So microwave radiation from space is the key evidence to prove the Big Bang theory. The problem was in the 1940s when they came up with this idea, nobody had the technology to measure microwaves from space. So people forgot about this. And then these two gentlemen came along. This is Arno Penzias on the right and Robert Wilson on the left. And they didn't know anything about this. They weren't really interested in the Big Bang. But what they had was what's called a radio telescope. That big object in the background is called a radio telescope. And what you do with a radio telescope is you point it up into the sky and you pick up radio waves. Every object in space doesn't just give out light, it gives out infrared, it gives out ultraviolet, it gives out X-rays, it gives out gamma rays, it gives out radio waves, it gives out everything. So by pointing this telescope at those objects, you can learn different things about the stars and galaxies. So they built this radio telescope, and before they pointed it at a galaxy, they pointed it at a bit of empty space. Because if you point it at empty space, you'll get nothing. And that's a good way to calibrate your equipment. But when they pointed their telescope at nothing, they got microwaves. Because microwaves are a type of radio wave. They pointed it somewhere else, they got microwaves. They switched it off, they switched it on again, they got microwaves. The next day, they got microwaves. Wherever, whenever they pointed this telescope, they got microwaves. And they were really annoyed. They had no idea where these microwaves were coming from. They checked the wiring, they checked their oscilloscopes, they climbed inside the funnel, they found there were 2 pigeons nesting there. And the pigeons had deposited what they called a white dielectric material. So they cleaned out the white dielectric material, still the microwaves kept on coming. And eventually, they would go to conferences and they would complain. They would say, we built this great telescope, everything's looking good except we get these really annoying microwaves. And eventually somebody who knew about the Big Bang theory and who knew about these predictions said, look, the microwaves you have detected are the microwaves from the Big Bang. They are the exact wavelength you would expect from the Big Bang. The only way to predict these microwaves is through the Big Bang. What they had accidentally discovered, their serendipitous discovery, was the echo of creation. And in a way, that was the turning point in the debate. Tommy Gold, who didn't like the Big Bang theory, had said previously, if you want me to believe in dinosaurs, show me a fossil. If you want me to believe in the Big Bang, show me a fossil. And this echo of creation is exactly the fossil that convinced him. And there was sort of another 10 years of research. This was 1964, this measurement was taken. There was another 10 years of research, of checking and double checking. But in the mid-1970s, they won the Nobel Prize. And they won the Nobel Prize for discovering the microwaves. And in a way, that was the official stamp of approval for the Big Bang theory. Now, let me see how we're doing for time. Oh, it's halfway through. Maybe now is a good time to stop. And then we can take some questions and just see how things go from there, maybe. Great. So I think somebody has a microphone. Should we have a discussion first? Yeah. Great. Great. Oh, sorry, man, I didn't see that, so I was looking over here. So we'll have a chat for about 10 minutes, and then we'll have plenty of time for questions.
Simon, I think people would be curious, how did you begin your adventure with science? Were you one of those kids with those science tests, sets?
Yeah, I think I've got a 2-year-old, almost 3-year-old boy, and they're interested. They're interested in everything. He stares up, the beautiful moonlit skies we've had in the last few days, and we stare up at the moon, and what's the moon made of, and where did it come from, and can we get to the moon? So children have a natural fascination. And I've often heard it said that scientists are people that grew up and never lost that childhood fascination, that curiosity. And I was good at maths, and I was good at the sort of technical areas of it as well. Ideally, I would love to have been a scientist. But when I was doing my PhD, I could just see there were other people who were smarter than me and quicker than me. And so I let them carry on and do the real science, and I now have a great time writing about science.
Did you have great teachers?
Yeah, teachers are really important. In England, in England there's a big problem, and I think the same is true in Western Europe and probably in America as well, is that if you've got a really good science background, then everybody wants to employ you. In the computer industry, in the IT industry, in finance, everybody wants scientists. And so very few scientists go into science teaching. And that means that fewer students are inspired, fewer scientists graduate, they're even more precious, they're even tempted away even to a greater extent. And so you have this downward spiral in Britain, which I don't think we're addressing. Whenever I come to India, I've been to some science festivals, I went to one in Mumbai last year, the enthusiasm, the number of people involved in those areas from a young age to an older age in technology and industry and universities is very inspiring for somebody, I think, from the West.
Well, we've had our problems. Our scientists have had serious problems. It's been quite controversial on how they're treated and the lack of facilities that they have to survive with. Tell me,
I think that's an important point. In Britain, we have absolutely top-rate laboratories. We have pretty good funding. The funding cuts. The British economy is in trouble, but they've protected science to some extent. But more and more of our people who are doing research are coming from overseas. So
yes,
the jobs that we're offering are being filled by people from around the world and not so much by British people, which is a tragedy. My background is Indian. I have a heart here in India as well, but I have a heart in England as well, and that's the land of Darwin and Newton and Faraday, and we're just not producing that same number of young people coming through with a passion for science.
I'm going to preempt, I think, a question which I would expect from the audience so that they can ask other questions. Sure. Where does God not fit in your Big Bang?
He doesn't fit in anywhere, I'm afraid. I think the great thing is that Lemaitre was religious. And for him, he had a role for God in his life, and he had clearly a dedicated faith. Galileo was incredibly religious, and he said, God gave me a brain, and he gave me a brain to understand how the universe works. And I think the question of the origin of the universe is a scientific question for me. And I think that's the only way to look at it. So there are some scientists who are religious, there are some scientists who aren't religious, but if they're good scientists, they will appreciate the Big Bang Theory, they will appreciate its flaws and its weaknesses, but they wouldn't look for a role for God in the Big Bang Theory, I don't think. And it's the same with, I'm not an evolutionary biologist, but again, I think it's the same thing. These are scientific questions. And there's a minor debate in Britain about this. I think most Christians in Britain would accept evolution and would accept cosmology in terms of science. But we have some fundamentalists who will argue for the teaching of creationism, who will argue for a literalist appreciation of religious texts and so on. But as a scientist, there's no role in researching the universe for a God.
And there's been always a controversy about the teaching of Darwin in schools.
No, there's not always been. No, I think when Darwin was alive, there was a dispute, obviously. There was a bitter argument. And then I think by the 1920s, he was buried in Westminster Abbey. He was accepted as a Christian when he died, even though maybe he wasn't a Christian himself. He had great atheist doubts towards the end of his life. But by the 1920s, every school in Britain taught evolution. In the 1930s.
In America, there's a controversy. There are religious people who object to Darwin being taught.
In America, it's a much more Christian country, and it's You can't run for president unless you're Christian. You can't, atheist is a dirty word almost. So for them, it's been and there have been long legal disputes and the Dover court case and the Scopes monkey trial and so on.
Yes.
We've not had any of that in Britain. There have been minor disputes with people trying to smuggle in creationist literature. But pretty quickly, educational boards will try and get rid of it. But as I say, the 20s, 30s, 40s, 50s, 60s, 70s, no dispute in Britain at all. Now there's a minor dispute. But it's yeah.
Can scientists have been looking at the Big Bang Theory as where did it all start? Are there any scientists who are looking at where we're going?
Yeah, I mean, the Big Bang, I've used the Big Bang model in a very loose way. For me, I use the term to explain how did we get to the universe we have today. So the universe, the Big Bang Theory can pretty impressively explain what happened in the moment after creation right up to where we are today. It can explain the origin of stars and galaxies. It can explain the origin of the elements that make up our bodies, although maybe that's not so much Big Bang, but nucleosynthesis and nuclear physics. But if the universe is expanding and the debris is flying apart, there are two options. Let's just say two options, really. Either, this is what I learned as a student, say 20 years ago. There are two options. Either the universe just flies apart forever, and it becomes less and less dense, and with less and less dense means less and less energy, and the universe dies. It becomes cold and desolate, and there's nothing here.
And how many billions of years would that take?
Oh, well, the longer you wait, the colder and deader it becomes, but it just carries on for eternity. Or gravity will pull everything back. Gravity can pull the galaxies back. So if the universe is dense enough, the galaxies can fly back into what's called a big crunch. And then the big crunch might be a big rebound, another big bang, big crunch, big bang, and so on. So those were the two hypotheses. Does it expand forever, or does it collapse? If it's expanding forever, it would still be slowing down, because gravity would begin to pull it back. But about 12 years ago, somebody said, let's measure this expansion. Is it slowing down? How much is it slowing down? And when they measured it, the universe is not slowing down. It's running away faster and faster and faster. And nobody understands that, because gravity should be pulling it back. And so we don't know what this force is, so they call it dark energy. I talked about dark matter. Dark energy is what's driving this expansion. And that's one of the big, if there are young people here today who are interested in physics and cosmology, I think in 10 years' time this will still be a big problem. What is dark energy? Why is the universe running away with itself?
Has there been any research on how this affects the movement of all the galaxies, affect the Earth in terms of affect humans?
Sure. I glossed over that very quickly. Within the galaxy, within our galaxy, the expansion is not really an issue, because gravity really binds our universe together very tightly. So I'm not expanding. I'm putting on a few pounds from time to time, but I'm not expanding in a Hubble sense. The Earth is not expanding. Our galaxy is not really expanding. In fact, our neighboring galaxies are coming towards us because the gravity is pulling them in. But once you go beyond our galaxy a certain distance, then everything really is expanding. Yeah.
Are you optimistic about other life on other planets?
Yeah, I think so. I think it just, there's something called the Drake equation, developed by an American astronomer, I think, where he says, this is the number of planets, this is the number of stars, this is the likelihood of water, this is the likelihood that the planet is not so far from the star, it's cold, not too close, it's going to boil, etc., etc. And it comes up with a probability of, is there life out there? And I think it's inevitable. The problem is that the galaxies are so far away, and the other stars in our galaxy are so far away, that whether we'll ever be able to communicate with them will be the problem. So yeah, I'm optimistic. I'm kind of optimistic we'll find some more interesting stuff on Mars as well.
Where they found water on Mars.
Yeah, I think there's strong evidence of water in the past, and probably evidence of frozen water in the caps as well. It's an exciting time to be doing science.
Should we open it up for questions?
Sure.
Should I go first or?
Go first. Yeah, I
Whoever
have a
has the
small
mic.
question. Do you have any answers as to what caused the Big Bang?
So what caused the Big Bang? So yes, so this kind of question, whenever I'm asked this question, I always tell a story. I hope you won't be offended, about St. Augustine. And somebody asked him the parallel question. They said, not what came before the Big Bang. They said, what was God doing before he created the universe? And St. Augustine scratched his head and said, he was creating hell for people who ask questions like you. So,
Okay.
but no, it's a very, very good question. It's a very good question. And people look at that. That's at the boundaries of our knowledge, obviously. And maybe there was a big crunch. Maybe this runaway phase we're seeing now is only temporary. Maybe the universe will slow down, collapse, crunch and Big Bang. That's one option. Another option is that universes can give birth to other universes. So if you have the right conditions, our universe could spawn a daughter universe, and our universe would be born from a mother universe. And so that's interesting, because then you have a family tree. And every universe will be different. Just like we're different from our parents, our universe will be different from our parent universe.
So,
And that's just one quick thing. So this is a very nice idea, because you have a multiverse, almost an infinity of different universes. And this helps explain why there's life, because we take for granted that gravity is the force it is. Gravity could be much stronger in our universe. If it was stronger, then the stars would collapse and there'd be no time for life to evolve.
There's some people in the front here.
If gravity was weaker, then the stars wouldn't form and we wouldn't have life. So how come gravity is just right for life? How come the magnetic force is just right for life? How come the nuclear force is just right for life? Well, if you have an infinity of universes, then some will be sterile, some will be lifeless, some will be born and die in an instant, but some will be just right for life. And obviously we're lucky enough to be born in one of those universes.
Yeah.
Lady just here.
Yes.
Hi. My name is Indra Chandrasekhar, and I'm a scientist turned writer as well. And I worked in serious molecular biophysics, computational chemistry for a long time on membranes. And people thought the natural thing to do when I started writing would be to do science writing, as you do so well. So mine is sort of a technical question. One of the reasons I didn't go into science writing was, for one, I really struggled with simplifying things and not oversimplifying them. And the second thing was that sometimes it's an awful lot of work. You really have to research your science as well, and it's fairly challenging. So my question to you is, A, how do you deal with the simplification, and B, do you work with scientific papers, or do you work on popular writing of science, you know?
So there are some people like Richard Dawkins or Stephen Jones or Martin Rees who are astronomers or evolutionary biologists or geneticists, and they write about their specialist area. So for them, research is not a problem because they're already world authorities in their area. I jump around. I'm a particle physicist by training, but I've written about cosmology. I've written about mathematics, I've written about alternative medicine, I've written about cryptography. So I have to spend at least 2 years researching. And that varies from reading some initial primary research papers, some summaries of research, talking to the scientists in particular. It's a range of different things. Also, I write from a historical perspective often. So again, I have to go back into the history as well. But that's part of the fun, is I spend 2 or 3 years learning of these subjects. And but then I don't really keep up to date. So I published Big Bang a few years ago, and I'm interested in the latest ideas on cosmology, but I'm probably not as up to speed as I should be. When it comes to simplification, I think I probably have an advantage in that when I learn about nucleosynthesis of the atoms in our body, I had to learn about that from scratch. And I try and remember what I found difficult, try and remember what I found interesting, and try and pass that on to the reader, because the reader is in pretty much the same position I'm in, that they're not a cosmologist. So in general, I tend to err on the side of giving too much information, and because I think the worst thing in the world is if I read a science book and I get confused, then I feel stupid, I feel angry, I feel annoyed. If the writer gives me too much information and I know it already, then I feel flattered, I feel kind of clever. So that I tend to err on that side.
Over here, and then when you're done, would you pass the mic to the young man next to you?
Am I connected? Am I connected?
I think so.
Good morning. My name is Charles Boville. I'm from London. When I was a small boy, I ran away frequently. And I took my own little universe with me. And invariably, I was very clear as to where my several destinations were on those several equations.
Would you hold the mic close to your mouth?
I knew exactly where I was going to go, and it wasn't more than about a quarter of a mile away on most occasions. The universe that you and I and everybody here shares is running away from us. Where is it going?
So the universe is expanding. What's it expanding into? One possibility is that it's infinite and therefore can just expand forever, because double infinity is still infinity. Another possibility is that the universe is wrapped around on itself like the surface of a balloon. We have a balloon as a two-dimensional surface in a three-dimensional space. But it's very hard to imagine this, but the universe could be a three-dimensional object wrapped around into a four-dimensional space. And then it just keeps expanding like a balloon that's blowing up. Now, if that theory is correct, if we look in that direction long enough, we might be able to see the back of our head, because the light would go all the way around the universe, or all the way around the universe. And people do look for that. People look for a certain pattern of galaxies over there, and if they see the same pattern of galaxies over there, then they know that somehow the universe is wrapped around on itself. But again, that's one of the boundary questions. And if there are young people today interested in cosmology, what shape is the universe? How is the universe expanding? That's exactly a very good question, but nobody really is pinned down.
Yeah.
Good morning, sir. My name is Deep. The question can be stupid because of my lack of knowledge, but I just want to ask. So when we read quantum physics, so it says that observer plays a part in formation of the reality. That's how the double-slit experiment and electron comes into form of particle, instead of probability cloud. So if we take that theory and into the, and we see as the Big Bang, then we need a neutral observer to make Big Bang a real. So, but Big Bang itself, it says that a starting point. So how can you mix two theories and say that who was the observer who has observed the Big Bang, and that's why it comes into existence? Because quantum physics really say that observer plays a part into reality. That's why Einstein told that I don't want to believe that if I'm not looking at the moon is not there. He was really confused by that. So I just want to know if we try to mix two theory.
I think what he's asking is that scientists are guessing.
No, I don't think that's what he's saying. No, no. It's a real thing in science that in quantum physics, if you want to look at something, you will inevitably change it. If I want to look at my hand, I need some light. And the light will heat my hand, so my hand will change. It will knock electrons off it, so my hand will change. If I take away all of the light, I can't see my hand. So observation will change what you see. Also, there's this idea of Schrodinger's cat, that you put a cat in a box with a vial of poison, and the poison is activated by a nuclear disintegration, and if you close the lid, is the cat dead or alive? In Newtonian sense, we say the cat it's dead or alive, we just don't know. In quantum physics, we say it exists in both states, a quantum superposition of dead and alive. And when we open the box, then by observing it, we collapse it into one of those two states. Now, this seems like mind games, it seems like philosophy, but it's very, very real. There are phenomena whereby if you continually look at the object, and you continually look at the phenomenon, you can inhibit the development of that phenomenon. So then the question is, how important is the role of the observer for the entire universe? If observers are important at the atomic level, is an observer important at the cosmic level? And I don't know, I'm afraid. That's not a question I can answer. One answer would be to say that I am an observer, and I can see you, I can see the stars, I can see the galaxies, and indirectly, I am here to observe the origin because I can see the consequences of it. So I don't think you necessarily need a God or an external observer. Our own consciousness might be enough, but it's not really a road that I'm familiar with, so I can't really add any more, I'm afraid.
And so I think just to elaborate on that, obviously there was no observer of the Big Bang, but it was observed in retrospect.
I think it's not an area that sort of philosophy of quantum mechanics is a very hotly disputed area, and one that that I don't know much about anyway, but that's exactly a good summary of the statement, yeah.
Who has the mic? Yeah, okay. Just give it to anyone, yeah.
Hello, I am B.L. Lashkari, a consulting metallurgist. My inquiry is this: you mentioned empty space, and is it this empty space is part of universal? And if universe is expanding, so where it is expanding? It is in the empty space or where?
Sure.
So I just want to know what is the empty space, and it must be a part of the cosmos also, empty space.
Sure, sure.
So where it is expanding?
Sure.
To whom it is expanding?
Sure. Could we pass, there's a young lad there with a blue sweatshirt. If we could go to him next, you've been very keen. The expanding into, I dealt with a little bit in the previous question. The universe is incredibly empty. The distances between us and the sun are enormous. The distances between the sun and the neighboring star are enormous. The distance between the galaxy and the next galaxy are enormous. The universe is fundamentally empty space with tiny pockets of matter. And within those tiny pockets of matter, tiny pockets of life, hopefully, like us. But even in space, we can't just ignore it, because that space plays a role. Einstein told us, if we look at an Einstein view of the universe, that space bends because of the mass that's in it. Mass tells space how to bend, and space tells matter how to move. So it's the space in a way that allows the galaxies to move and to dance and to expand. But space is very much part of the universe, and it's that space that allows us to dictate the movements of the galaxies.
Hi, I'm Siddharth. My question is, when you said that Big Bang requires the existence of microwaves, and then microwaves were actually found, then it suggested that it could have come from there. So it seems like a converse fallacy, that if statement A implies B and statement B actually exists, we tend to say that statement A was true, while it could also have come from some other source, right, the microwaves. So this is one question, and another is, what are the implications of Big Bang other than the theological debates, and why are we interested in other life forms in other parts of the universe? What are we going to achieve from that?
Okay, let me just go back one stage, is that I said initially the Big Bang theory was rejected. Everybody said this is rubbish, go away, we don't like this theory. And bit by bit, more and more evidence was built up. And after about 50 years, we have what's called a paradigm shift, where there was so much evidence that scientists said, we now accept the Big Bang theory. It's the same with climate change. If you go back 50 years, and you talked about climate change by carbon dioxide and human emissions, people say, no, that's rubbish. But bit by bit, we have so much evidence now that the paradigm has shifted, and the overwhelming evidence tells us that climate change is happening, it's man-made, it's real, and it's going to be a problem. So that's what happened with the Big Bang. Now, when somebody got up at a conference in 1965, 66 and said, look, these are the microwaves, and these microwaves came from the Big Bang, somebody would have said, why do we believe you? Now, I think the first thing is that somebody would say, this was predicted beforehand. When you predict something and it comes true, that's a very, very strong evidence that your theory is strong. Prediction is an incredibly important part of developing a scientific model. Secondly, somebody might say, but is there another explanation for the microwaves, which is what you're saying? And people have tried to come up with other ideas. One idea is that in empty space, we talked a little bit about empty space, you do find very small iron crystals. And one theory that was put forward was that starlight can be absorbed by iron crystals, and the iron crystals can re-radiate them as microwaves. So maybe we're being fooled. And people looked at that, they explored it, but when you look at the distribution of the spectrum you would expect of microwaves, it's not what we see. What we see is exactly what you would expect from the Big Bang. So scientists are their own worst critics. If you go to a scientific conference, it's very aggressive, it's very confrontational, hopefully done in the right spirit. But people put up their ideas and other people try and knock them down and batter them. But if you can survive them, and that's what's happened with the microwave theory, then you add it to your body of knowledge. And that's why, in the end, there are other reasons why people believe in the Big Bang theory, which I haven't come on to. But it's that mountain of consistent evidence that means we now take it seriously. Oh, the implication of the Big Bang? No real implication other than how cool is it that we know where the universe came from? You know, we're curious human beings. And I think it's just the eternal question. And it's one of the questions in England. We were talking about science and science funding. Should we put money into Big Bang physics? Should we put money into CERN? Should we put money into silicon chips? And I think you have to put money into these fundamental areas of research for 3 reasons. One is that I got interested in physics because of Big Bang and particle physics. A lot of my friends did as well. Now, they go off and they work in industry and they work in technology. But the inspiration came from these big ideas. So studying and researching these big ideas pulls in young people. Secondly, technology comes out of these areas. If you want to detect the Big Bang, you need the most sensitive detectors in the world. And those detectors then find uses in hospitals and other places. In CERN, they developed the World Wide Web, which has transformed economies, technologies, the way we interact socially, and so on. And thirdly, just for the cultural benefit of knowing the answers to these questions.
My question is about extraterrestrial life. Do you think that given the right conditions, there could be human life in other planets and galaxies, given the right conditions, hydrogen, nitrogen, oxygen, methane?
Yeah, I think it's almost inevitable, because
so that alien life would not be the little green men with horns. It would be human beings in some other planet.
I don't know if there will be human beings in the you know, if a million years ago, I don't know, again, I'm not a human biologist or anthropologist, but I get the impression that there was a time about 1 million years ago when we were a very small tribe of people in East Africa, and 2 or 3 massive droughts could have wiped out the human population, and then another evolutionary branch would have extended instead of humans. So our own existence is very, very fragile. And our own existence on this planet is only momentary. We've been around here for 100,000 years. If we're lucky, we might be around for another 100,000 years. But then some other life form will evolve and take over. So whenever we make contact with another civilization, what life form will be in control or will have intelligence at that time is impossible to tell, but I guess it will be very, very different. It will be a different gravitation, a different environment. It may not even be carbon-based. It could be maybe silicon-based or some other form. So yeah, no, I think in a way it's more fun to imagine all the weird and wonderful possible forms of life that are out there rather than constraining our hopes of them being human.
What about the antimatter that was created during the Big Bang?
Okay, so I think we're coming up to 11 o'clock now, so maybe the last question. So, we can switch one more question after this. But yeah, so in physics and in particle physics, when you create a matter particle, you create an antimatter particle. So in the Big Bang, we should have had all of this matter and all of this antimatter. So the question is, where is the antimatter? And there are two possibilities. One is that the antimatter is out there in different parts of the universe. So this is an area that's dense in matter. Somewhere over there, there's an area dense in antimatter. More likely, in experiments done at CERN, we know there's a slight imbalance. Antimatter and matter are not perfectly symmetric. And there are some, there are some collisions, some interactions, which slightly favor matter. And so it could be that in the early universe there were 1 billion matter particles and a billion minus 1 antimatter particles. They all annihilated except the one left over here. So what we are is the leftovers of a massive creation and a massive annihilation. That what I think cosmologists are pretty confident about that. But there's still work to be done.
One last one.
Yeah, do you think there'll be a theory which connects general relativity and quantum physics? And if yes, would it lead to possibly the theory of everything, which has been our quest?
Yeah, so there is this big problem in physics, which is that Einstein, there have been two revolutions in the 20th century. One is Einstein's theory of relativity, and general relativity in particular, which explains gravity. And that's fundamental to cosmology because gravity tells how all the planets and the stars move. And then we have quantum physics. And quantum physics is the other great revolution which explains the electric force, the electromagnetic force, the nuclear forces and so on. And this explains how all the nuclear reactions inside the stars work. But so far nobody has been able to marry the two. Worse still, the two theories are almost in conflict. And this is again at the forefront of physics. There has to be a resolution. There has to be a resolution. Whether we will find it, I don't know. And Sir Martin Rees, the Astronomer Royal, said, you know, why should we be so arrogant to think that our brains are smart enough to resolve this disparity? Maybe our brains have not evolved enough to comprehend that. Maybe it's just that we don't have the mathematics yet to comprehend it. Maybe somebody in this room, somebody in this venue will go on to resolve it. But there has to be a resolution. The universe doesn't throw up puzzles just for the sake of it. So I'm optimistic, but you're right, this is a big problem. Yeah, string theory is one of the best candidates for resolving the two. String theory suggests that instead of there being just 4 dimensions, there are extra dimensions, and particles exist in these extra dimensions, and that in these extra dimensions, we would be able to, one, exhibit the properties that we see in general relativity, and also generate the properties which we are familiar with in quantum mechanics. So string theory is one possibility. And some people are critical of string theory because it's been around for 40 years and still isn't successful. I'm more optimistic because it keeps coming back, which makes me think that there's something there worth, that ultimately will come to show a reality that makes sense to us. But the key thing, which comes back to your point, is that string theory needs to predict something. If string theory says there is a particle with this mass and you will find it here, and we go out and we look for it and we find it there, then we will begin to think that string theory is real. At the moment, it's a theory without any experimental verification or prediction.
Before I thank Simon, I'd like to thank the audience. You really had some lovely questions, and it was a great discussion. Simon, thank you for expanding our horizons into space and various galaxies. It was lovely.
Thank you very much for coming. It's been a pleasure to be here. Thank you.
Well, many thanks, Simon Singh and Madhu Trehan, for that fascinating session, like Madhu pointed out. Ladies